Good to see you, welcome back. Here we are with the part 2 Doom tutorial, and thank you so much for all the nice comments from part 1, and I'm so happy to see what you made after watching the part 1 tutorial, like converting the code to other languages like Java and even porting part of it to the old Tandy computer. That is very impressive and it's so cool to see. And after making some optimizations, I was able to port part 1 to the old Game Boy Advance myself. And you might want to rewatch part 1, but here's just a quick reminder on how the game engine works. A wall is made up of 2 points at X and Y coordinates. We divide those numbers by their distance in space. So larger numbers shrinks closer to 0, but we shift that point to the center of the screen to create a 1-point perspective. And several enclosed walls form a sector. Those sector walls are always drawn with vertical lines, and we save the back walls values to connect and form a flat surface. And if we do this for every frame, it will look 3D. And I made something just for you. I created a level editor I called Grid 2D, so you can better design your own levels, save it, and load that file into the game engine. And I'll also be updating the Grid program to have more features, and I'll give you a link to download the Part 1 code. I can also share the GBA port, and of course the Grid 2D program. And the thank you button is located right here and here. And with your thank yous, I'll continue to make updates and more tutorials, so thank you so much for your support. Let's start with a fresh blank folder in the Part 1 tutorial, either the code you created when following along, or downloaded from the link below. The first thing I want to update is how we're actually loading in the sectors and walls. We were writing the array numbers by hand, and these 2 arrays loaded in the initialize function. And I wanted to make something better for you. So I designed the Grid program. Now it's no Unreal Engine, but it is capable and it can do what we need it to do, which is choose a wall texture and a surface texture, tile those if needed, set the bottom and the top height of the sector, then click to add lines to connect to form the sector. Then you can right click to move and make adjustments to those points. And this does have limitations. I made it so you have to draw in a counterclockwise way to prevent complications in the code. And the sectors need to be convex shaped. Since we aren't sorting the walls, we're just using backface culling. Then I made it so you can select a sector and go back and make adjustments to the surface or individual walls. Or if you don't like it, you can delete the sector. And this is just version 1, and I will add more and I can make updates with your feedback. And I can make a separate video to explain this code step by step, but this tutorial is about the Doom game engine. So this level editor just saves out a text file that we need, which is the number of sectors, then those sector variables, then the number of walls, and then those wall variables. And I made it save the player position too. So you can technically make edits here with the text editor. So both the Grid and Part 2 code will eventually read from a folder called Textures. And you can create your own, but I'll link below to where I found these really cool game textures. And I select just the texture I want and I save it out as a bitmap. And I'll also link to this really great browser converter. It makes it very easy. Just drag and drop the texture. We want decimal, 24-bit RGB, separate bytes, and you can even see the title here. So let's make it say a constant char and our texture name. And every pixel is made up of 3 numbers, the red, green, and blue values that range from 0 to 255. Save it and continue doing this with the other textures that you want. And if you want to make edits to the Grid program, you'll need to recompile, but you'll also need these textures for the background and the number array. But again, you really don't need to compile the Grid, just run the program and save out the levels. But let's open the Grid code side by side. Let's save time by copying the included texture links and the array variables, since both programs are going to use the same textures. So we thankfully no longer need to load arrays since the Grid saves out the data automatically. And the Grid save file has a few more variables than we have at this current time, so let's add the new wall struct variables for texturing it later. We can increase the array size, and do the same for the sector struct. So these are our 2 main arrays that our game engine uses, which is very similar to how the Duke Nukem 3D build engine works. And we need a new struct to hold these new texture variables. And I'll go more in depth on how these new additions work coming up later, but for now, let's just add them so our Grid file will import into our new game engine. And here's the code I wrote to save out the sectors and walls. And here's the code where I load in that saved data. So let's copy the load function into our game engine. Then we can call this load function when we press one of the keyboard buttons. And also, several of you commented that the =1 isn't necessary, and you're right, so we can remove it. Now the enter button has a numerical value of 13, so every time I press the enter button, we can call the load function to read in the save file. And you can of course set it to any key that you want, but for me I'm going to use the enter button. So let's test it out to see if it works. Compile the code, and then press the enter button, and perfect. The sector that we drew in the Grid exported and imported into our game engine correctly. We can even open the programs side by side, save, and then load into our game engine, so we can make edits almost in real time. This is so much better than coding by hand. This is great to see both the two-dimensional grid view and the 3D view. So we actually have a small correction we need to make to our game engine, and it's only noticeable if you raise the bottom to a value higher than 0, so you can see the top is actually twice as tall as it should be. And this is because I was trying to prevent recalculating the top line, but really we do need to calculate it on its own. Compile, and there, that's how it's supposed to look. And by the way, I'm holding the key M and S to rise up, and I'm tapping D to look down, or I can hold M and W to move down and tap A to look up. And there's so much more I want to show you, so hang in there and hope you enjoy the rest of the tutorial. And it's worth mentioning, if you minimize the console window and try to compile, it will be grayed out, so make sure you close the window in order to compile. I want to make an important update from part 1. I'm going to create a long sector using our grid program and load it into our game engine. Our code will work fine for small sectors, but you can see long sectors, the floor will actually clip and disappear. This is because we're drawing the back faces first, saving that edge, and then drawing the front faces vertically up to that previously saved edge, which is a problem if the wall behind us is clipped and never drawn. And it's more efficient to draw the front faces first, because sometimes that's all you need to draw. So, in our draw 3D function, I want to give this loop a better name, making it more clear that we first loop to draw the front and then the back faces, if needed. And we need another variable called cycles to tell the for loop how many times to cycle, once or twice. We now want to flip the walls on the second loop to collect the back-facing edge. And we need to clear and set the surface variables to the top or bottom of the screen in case we never draw the clipped wall. We can default to the screen edge. And this X now needs to be defined. So the final calculated and projected wall points are here, but I now want to pass the sector and wall number and our new front-back variable. And we no longer need to invert the surface number, which did work, but it was kind of confusing. Let's update the function parameters to match. Remember that we were clipping to 1 to test the clipping, but we now know that the clipping works. So let's update the clipping to end at the screen's edge. And let's make this cleaner and say if the front-back variable is 0, the first loop, we are drawing the front-facing walls. And we can also store the bottom edge Y value for the next loop surface. And loop 2 is similar, except we draw from this edge up to the back-facing wall to create that flat surface. Let's compile and see if this works. And that is perfect, so we can now skip walls that are behind us. We don't have to calculate them, but we can still draw the surface down to the screen edge. So the code to calculate this sector is now pretty solid, but it could use some textures. So far, we're including the texture arrays, and we made a struct to hold them, but we need to load the struct in the initialize function. To do that, we set the texture name, height, and width. Luckily, the grid program that I wrote is very similar, and I've already done this code in that, so we can simply copy that to save us time. Our textures are saved as RGB pixels, so we need to update this function either by creating millions of unique if statements, or, better idea, let's now pass in a red, green, and blue value. And I want to rename it to drawPixel. So let's update the function here in the clear background. RGB will be 0, 60, 130, and where we're drawing the walls and surface routine. How about green walls and a red surface just for now? So the foundation for texturing is now all set. We can see our RGB pixel function is working great. So up next, we're finally going to add textures to these walls. I want to create a function to test if our textures are working correctly, and we'll be using this code later too. So let's create a double for loop to cycle through this specific texture's dimensions. Since the texture we created is actually stored in one long array, we can pretend like there's an X and Y coordinate if we times the Y by the texture's width. So we can, in a way, skip down to any line and then add the X value to locate that pixel. It becomes like that old Battleship game, if you remember, where you guess a letter and a number and then they, sink your ship and you lose, and yeah, I hate this game actually. Anyway. So our code will look something like this: Y times texture's width plus X. Remember, we're saving 3 values per pixel, red, green, and blue. So we need to times X and Y by 3 to skip to the next pixel. And since we skip by 3, we can add 1 to find the green value, plus 2 to find the blue value. And finally, we can plot this RGB at coordinate B7, X and Y. And this function will just sit here and do nothing unless we call on it in the display function. It works, it's just upside down. And we can fix this by saving the texture flipped, or we can use math to invert the Y value. So far, the Y values will go from 0 to 15, but if we start from 15 and subtract Y, it will return the inverse from 15 down to 0, flipping the texture to look correct. And you can change the texture array number to display a different texture. And now we have the power to summon any texture we want simply by changing the array number. So let's turn this off and go back to our draw wall function to make something similar by holding this particular wall's texture number and create two new variables to hold the horizontal starting value and horizontal step value. So we want to start drawing the first horizontal pixel at 0, but step a calculated distance each vertical column. And we calculate this step with the texture's width divided by the distance of the x values. So let's plug in some numbers to test this theory. So if the distance equals 8, we step 2 times per line. 16 is perfect, 1 step every vertical line. 32 we take half a step every line, and so on. The vertical line is the same, just make sure to update the variable names and the y distance. And here is where we're drawing the normal wall, so let's recycle our test texture code and place it here. Update the texture variable name and place the starting vertical texture value in the pixel. Then we need to add the step amount. Same for the horizontal start and step, but outside the while loop. Compile to see our texture taking a step in the right direction, but take a closer look and you can see the texture looks fine off-screen right, but off-screen left causes some distortion. Which actually makes sense since we're always starting the pixel at 0, but I think we can fix this. If x1 is less than 0, we can times the step by the amount. An example, if x1 is, let's say, -42, we times negative step by -42, which will update the starting value to now be a +42 instead of the starting 0. Update the y in the same way, and let's compile to see how it looks. The texture clipping now looks and acts correctly, the way it should be. We're making great progress, and up next, let's add automatic shadows and texture tiling. So I want to show you this code in the grid file where I'm calculating the angle of the wall to determine a shade value. So we can subtract this value from the RGB of our wall. And since we are subtracting, we now have the possibility to dip below 0, so we want to prevent that with an if statement. So let's compile, and we can see the shading on the wall. And if it's a little too intense, we can divide that shading in half to soften the shadows. And people from the part 1 tutorial should find this much better than manually coding in each wall shading. So our horizontal texture step value is currently using our texture's width. But what happens if we multiply this number? The value will now step outside of our texture array, so let's wrap it around by using the modular operator. This will make our texture tile in the horizontal direction. And the grid program will save out this tile data and load it into our game engine using the wall's U variable. In 3D graphics, U and V are used as the X and Y for textures, since X and Y was already taken. Let's set up the vertical V tiling the same way and see how this looks. This is so great. We can now tile textures to better fit on narrow, flat, or even stretched out walls. And we can now test this in the grid program, save it out and load it into our game engine to see it working in almost real time. Now this part is exciting. Let's create floors, which will eventually become our top and bottom surfaces. And this time our double for loop will start from negative half the screen's dimensions, and I'll show you why. So check out this neat trick. If we calculate the pixel's value shifted over half the screen, that puts the origin, aka coordinate 0, 0, in the center of the screen. And if we divide the x value by the y value, that number will shrink closer to 0, the center of the screen. Then, right before we draw the pixel, we shift the value back into place, and we now have a 1-point perspective. So fx and fy are our floor coordinates in the world space using that division trick. Make sure the compiler knows that it's a float value, and to alternate colors, let's use the if statement to check if the y and the x are both even. Pushing the pixel back into our screen, draw red for even, green for odd. So let's add floors to the display function and let's just see what we've got. And we've got something. It ain't a lot, but it ain't nothing. The right side looks pretty good, but the center and the left don't. These are negative values, so let's prevent that with an if statement and add 1 for accuracy. And that looks like floors to me. We have a nice checkerboard pattern in a 1-point perspective. And changing this 200 value alters the field of view, but I chose 200 since that's the field of view that we're using for the sectors and the walls. So let's try to keep it consistent. But we can do more. Let's create a variable to look up and down. And to help prevent dividing by 0, let's hold the denominator as z and add our new variable to offset the horizon line. Our player already has a variable to look up and down, so let's reuse that. We can now see the horizon line shifting, creating the illusion that the player is looking on the floor or looking up at the ceiling. And let's try to prevent drawing above the screen. And also, we only need to draw halfway up to 0, which will remove the unwanted ceiling. And some of you might notice we have a small problem to fix. we need to shift the top y value by our new variable. And there we go, and that looks pretty cool so far. Let's prevent dividing by 0. And next we want to rotate the floor point around the origin using sine, cosine, and our player's rotation. And let's make sure we update using the new rotation variables. And nice, we can actually look around. It's getting better and better, but now we need to actually move around in this world. And this is actually pretty easy, since all we need to do is, after we rotate, offset those points by our player's position. I'm dividing by 30 for now just to help slow it down, but we'll make this division a little more accurate later on. But for now, you can see we can look around, we can move forward, we can look up and down to the floor, and it's all done with simple math tricks to scale the pixels to the origin and then shift everything back to the center of our screen. And you don't have to do this next part, but I'm really excited to show you this neat trick. Okay, so the background color is RGB 060 130, right? So if we just change the red to 255 on half the squares, it'll look something like this. Now if we cut the red value in half, it's gonna fade or look closer to the background color. And you might see where I'm going with this. What if we scale the red value by the distance of the y? So divide y by half of our screen's dimension and subtract that from 255. That will create a value from 0 to 1 that we can times by 255. Oh my god, how cool does that look? The fog will help prevent you from drawing any geometry beyond that point. This also helps clean up that bad pixelation that we had towards the horizon line, and it helps create a sense of depth in the world. Really cool trick that we're not going to use, so let's revert back. Well, I guess we could implement this later, but in part 3. But I really wanted to show you that. Okay, and another cool trick we can do is prevent unwanted floor pixels. So, if the world's rotated point is below 0 or above 5, we can skip it, we're just not going to draw it. So this will create a very isolated small square. And of course, we want to be able to move up and down, so how can we do that? What if we scale down the floor's x and y value by cutting it in half? Let's see what that looks like. So the floor scales up, making it look as if we're closer to it. So if we use a smaller value, it will make the floor look even closer. And vice versa. If we use a large value, it'll scale it down, making it look as if we're further away or above the floor. So let's create a similar variable, but called move up and down, using our player's current z height. And I want to invert the look up and down, which makes sense to me. Let's see how it looks, and that looks pretty cool. We can move up and down, but we can't see it from underneath. The for loop will just end and never draw below. So we can fix this. I first want to create a y starting and a y ending variable to replace it, and alone this won't change anything. But if we check if our move variable is below 0, aka underneath the floor, let's update the y start and ending value, in a way inverting it to almost be like the ceiling again. And check that out. I think that looks pretty cool. It looks and acts as if it was a real floor. So next we need to implement this into our sectors so we actually have a top and bottom surface. Alright, we are almost there. Let's turn on the 3D and turn off the floors function, copy this code so we can paste it in our draw walls function where we were drawing the surfaces. And we don't need to cycle through the x values since this is already being done for the walls. So we can remove our x for loop, but we still need to add that negative x offset for perspective. So let's replace and update with our new x2 variable. I want to consolidate these variables and add a new one called wall offset. And I'll move these two if statements down here. And we no longer need this check, so that floor needs to be raised to the same height of the sector. So save that here and apply it to the move up down variable like this. Update the y starting and ending variable. And we don't need to limit the square boundaries, the sector walls will be the limiting factor. Compile, and we have something. It ain't a lot, but it ain't nothing. It does slide around, and the angle seems to be off. And there's probably a really nice formula to calculate this, but I found my values through trial and error. I found that a 6.2 multiplier for the look up and down, and 60 for the player offset worked really well for me. And that looks pretty good to me. It actually stays pretty well, but the tiling seems a little bit too big. So we can add a new variable called tiling, and we can use the sector surface scale, which looked best multiplied by 7 to me. So we need to apply this to the move up and down and player offset variables to match their offsets. And we now want to add textures. So let's hold that sector texture number and draw this similar to how we're drawing the walls by holding the pixel location, separating the RGB values, and drawing it at coordinate XY and adding that offset to bring it back from the origin to our screen. So finally we can test out our hard work. So let's just draw a simple square sector and save and load it into our game engine. And that's it, our surface texture and tile works. It's the same for the bottom, looks pretty good to me, And let's just change the texture and the tiling to test it all out. So you may want more or less tiling to match the scale you want. And note that the repeating edges like the grass texture will look best when they're tiled since they will hide the seams. And I have so much more I want to show you. So instead of the painter's algorithm, we should switch the BSP and portals to help break up and draw the screen without overdrawing. Oh, and there's collision detection, which is done in a really fascinating and simple way. We can add sector animations to have different platforms and moving walls. But I will save that and more for part 3. And I like that we built the game engine ourselves from the ground up so we know how it works. And please share with me what you make from this tutorial so I can add it to the beginning of the next video. This has been a lot of fun. Thank you so much for watching, and let's hang out again sometime. See you next time.